The next module is called generic programming, and generic programming in C++ is called template programming, and it's another programming model, programming paradigm as people call it, and we want to give an introduction to the whole spectrum of what you can do with generic programming techniques in C++. And it's a different way of thinking from object-oriented programming. C++ templates were around from early 90s and were pretty crude at the time because they were still in development and still hadn't been worked out properly. Microsoft didn't even have templates. They had sort of macros, which was pretty painful. One company called Borland did have templates, and I've been working myself with C++ templates since about 1992, when I worked on the option pricing risk management system, first generation. So on the bleeding edge. Now this first slide will have to do with just motivating generic programming. So let's start. Okay, so the goals are: become acquainted with the generic programming model. Now, why do you need to become acquainted? Because most programmers have now become acquainted with object-oriented programming. If you've taken my previous sections of the course, you know that you've got classes and you create instances of classes, and you can have inheritance, you can have composition, and so on. You can have all of this with generics as well, but it's a bit different, as we shall see in a moment. Just a general remark about template programming, generic programming in finance. There was a questionnaire and a bit of a survey done to see how much did programmers know about programming in generics and templates. 55% of the respondents said that they knew C++, whatever that's supposed to mean, but only 12.8% only knew STL, which is the standard template library, which is pretty strange. So you can start discussing if you're not using the standard template library for your data containers and algorithms, what are you doing? Maybe you're reinventing the wheel. Okay, so the goals are to acquaint people with the way of thinking in generic programming, of course, and to actually get you up and running using template classes, creating template classes maybe later on, and in particular, which is going to be more important, is learn the main functionality in the standard template library, which is part of C++, and that's very important. And we've got lots of examples for you and so on. And of course, the object-oriented way of programming with inheritance and all of this sort of stuff can be combined with generic programming. So you can have generic classes, let's say, which can be inherited from each other, composition. So it's not a question of either or. It's not Boolean logic, which some people think. I use OOP, I don't use generic programming, which is a bit of a silly comment. You combine each one depending on the situation you're confronted with at that moment in time. Okay, so let's take a very global overview first of all, just to get you warmed up. So this is warming up. The object-oriented way of programming is the following. It's got to do with the encapsulation principle, of course. You've got classes, in other words, and classes have data and functions. And you create instances of classes. These are called objects, and you've got inheritance. So that's basically it. So you've got classes, encapsulation, and inheritance. And that's the way your way of thinking. Generic programming, on the other hand, is you've got data. You look at data takes a higher priority. It takes a high level stage. So you've got data. So you're looking at data, and you're looking at algorithms on the data. So it's a bit of a different mindset, you might say. The most important part about the data is it's generic. Now, what do I mean by generic? It's deferred. You don't know what the data is. It's not a double, it's not a point, it's not an option. It's some data which will be instantiated, as it were, later on. So that's very important. And this is called template programming. And so we create classes and code and functions in which the data types are not specific data types like a double and an int, as I've said, but they are generic types. And we normally give it a name T. Could be called anything. Could be called N or TT or T1 or whatever. So this is what we're going to motivate in a moment. Why do you need it? Because C++ is a multi-paradigm language. In particular, it supports the generic programming model, and again in particular in the STL, standard template library, the Boost library, which we'll talk about later, and you can create your own template classes, which I do quite a lot. Now, okay, so let's see if I will try to make a distinction, try to show you what the distinction is between object-oriented programming and generic programming. So we've got classes and inheritance. So you've got classes and inheritance I've talked about. That's pretty familiar to you now. We've got so-called the subtype polymorphism again. You remember the virtual functions and the pure virtual functions in your base classes. These are the interface requirements, the virtual functions. So most programmers, C++ programmers, know this technique and they actually use it, which is fine. But as you probably see here, there's not much mention of the data that you're actually operating on. Generic programming, on the other hand, promotes to data structures to center stage, as it were. So you've got a data structure which is generic, and you've got algorithms working on the data structure. So if I just I'm going to type in something here. I'll show you immediately syntax. In STL, for example, we've got a data structure called a vector. Okay, the vector, let me just type it in just to motivate what's going on. So let's come back to the slideshow. So I'm editing in real time. So I've got a data structure T. T can be anything. It's delayed, it's generic, it's nothing, it's really nothing at the moment. And the algorithms on the vector, what kinds of algorithms can you imagine? It's a mathematical operation. Maybe you have to create a vector of a certain size. You can index, you can access the elements of the vector using an indexing operator, for example, and so on and so forth. But T is can be anything. Later on we say, wait a minute, I'm working with vectors of doubles, so you replace the T by a double. So you see here that your class is a vector, just like good old object-oriented stuff, but there's an extra level of indirection here to state. Here's my data structure. Okay. So the generic programming uses abstract requirements specifications. So you have a bunch of data, and you've got the functions on your generic class, for example. In contrast to subtype polymorphism, this is called parametric polymorphism. So when you're working with a vector of T's, all the T classes, or the instantiations as it were, should have the same kinds of functions. So it's a bit of a reusability, but at a different level and different from good old object-oriented programming. Okay, so that's a bit of computer science jargon. In computer science, at least in the old days, people learned about abstract data types. Abstract data types are data plus algorithms on the data. So like the vector here just a moment ago. And in contrast to object-oriented programming, a consequence in C++ is the templates and generic programming classes and functions tend to be more efficient than object-oriented code because of its compile time. Yeah, and we'll see in a moment why. Whereas object-oriented programming can be runtime using virtual tables, virtual functions, for example. Okay, so let's just take a very simple example of object-oriented programming. I've got a base class here. It's just to motivate. Here's a base class, two-dimensional shapes. It's got a draw function, which is pure virtual, of course. I've got a line as a derived class of shape, and I've got a circle as a derived class of shape. And I've got a draw function. It's simple, just draw line, see out line, see out circle. That's fine. Now I've got a function to draw a list of shape pointer, so it's a bit of a forward reference. List is an STL class, in fact, where the template parameter has been replaced by shape pointer. It's a pointer to a shape. And if I go back to my vector here, you see t. In our particular case, is a list of t's instantiated for t to be a shape pointer, but it's the same idea. Okay, so it's a bit of a forward reference, but basically what I'm saying is the following. What I do is I've got an iterator, which is like an enumerator it. So I iterate from the beginning of my list to the end of my list, basically, and I draw each element in the list, whatever it might be. So that's real object-oriented programming. You see here that we've got hard-coded classes here. So if you want your draw function to work for something else, another class hierarchy like an option hierarchy or an instrument hierarchy, I have to change the source code and recompile, and I've got the duplicate code because I've got one function draw which accepts a list of shape pointers, and another function draw which presumably accepts a list of option prices or something, option classes. Okay, so just a few remarks. It's just a good old object-oriented way, because we create the base class, in this particular case shape, and the derived classes implement certain functions. It's got runtime behavior. It's the so-called vtable. It's not very reusable code, and not because it's a simple function. That's not what I'm saying. I'm saying is that this shape here makes everything really hard-coded. So it's basically, actually what you'd like is just a list of any old objects, generic objects, and of course the generic object should have a draw function maybe, but I'd like to generalize it a bit. So let's go to the following. Let's say I cannot apply it to another hierarchy, which is a bit more technical hierarchy, but valves in process control systems and oil rigs and so on. You've got valves, so you want to draw a valve for some reason. It's a silly example, but it's good for illustrative purposes. I got ball valves, I got check valves, and all sorts of valves which open and close. But I want to draw a valve, so this one guy is a virtual function here, pure virtual, and each valve has its own draw function. So what would I need to do if I wanted to draw a list of valves, so all the valves in my power plant or something? I would have to change the code here, you see, and replace shape by valve, and everything would probably work okay, because every element in your list has a draw function. In other words, every valve, which is not really what I want. So I want to do the following. I'm now going to create a function called draw, and I'm working with vectors now, so I want to work with vectors just for a moment. A draw function which has a drawable thing as parameter. So drawable thing is nothing, it's just a generic parameter. So if you think about everything generically, I've got a vector of drawable things, which are just my iterator, and I go from the beginning of my vector v to the end of my vector v, and I just call it draw every time. Okay, so I keep drawing. So this is very generic, you see. So in the moment it will work with valves and shapes, because when you replace drawable thing by shape or valve, it's like a macro substitution. The drawable thing will be replaced by the corresponding class, and valves and shapes have a draw function. So that's nice. In other words, we only create this function once, and you instantiate it using the classes that you want. There's no free lunch, of course, because it's assuming here in the body of the code that your drawable things, the instantiations thereof, will have a draw function. Otherwise it doesn't work. So there's no free lunch. So some features of the solution are the following. It works with any class that implements a draw function. That's really nice. So your class doesn't even have to be derived from shape or valve or anything. So long as it has a draw function, you're okay. Now here's the big culture shock. Now this is an example of a policy. What do I mean, a policy? Here's a function. It means the following. I've got a function called draw, which works with any instantiation of drawable things, so any class, so long it has a draw function, which is nice. It's compile time behavior. Why is it compile time behavior? You'll see in a moment because when you replace drawable thing by the your own shape, everything gets replaced, as it were, and it's recompiled, so it's fast. The code is reusable, and it depends on the standard interface. What do I mean? I write this code once, and the standard interface is draw, so you're assuming that if you want to use, the policy is, the contract is, if you want to use the draw function, you have to, your classes which are going to be vectors of your classes have to have a draw function. So that's just the way it is. So let's take some examples using the hierarchy. I create a number of valves which are derived class objects of the base class. I create my vector of valve pointers. This should be fairly well known at this moment in time, because you know how to assign a pointer from a base class to an address of a derived class. So you put some things into your vector. We'll talk about vectors later on in STL, and we just call the function draw. Similarly for shapes, of course, but it's the same function. So the function here I call draw is the same as the function I called here in shapes. So there's no duplicate code. Traditional way of working would be the first approach would be just a list of shape pointers. I push the some lines and circles onto my figure, and I just call the draw function. So that's a bit old-fashioned. Okay, so just a general remark on comparing object-oriented programming with generic programming. Virtual functions, which is the lifeblood, you might say, of object-oriented programming, subtype polymorphism. These are certainly slower than function templates. So the template functions are faster. But the question is, do you want runtime behavior, or do you want compile time behavior? That's basically what we're saying. One remark is here, let me go back to my code again. Still in the motivation phase yet, but you can imagine the following. Let's say I've got a draw function, and I replace drawable by vector, by valve, and drawable by shapes. Every time you replace the generic parameter here, code is generated. So you've got twice as much code in principle. So, but is that a problem? Probably not nowadays. But you do get code bloat. Reusability. Yeah, if you use too much inheritance, you're not so reusable anymore. But we discussed this topic before. And generic programming, it's not even in its vocabulary. When you start thinking generically, you're not really thinking about inheritance. You're thinking about, I've got abstract data and I've got algorithms on the data. Okay. So what I'm saying is here, and this holds for, I must say, most of the programmers I've met in the last 40 years, 30 years, 20 years in C++, most of them use object-oriented stuff and very little template stuff, and certainly not STL and Boost. So maybe it's because people think of inheritance hierarchies, but now we have to think about a bit differently. We're thinking about contracts between abstract data types. Again, let me go back to my code. I'm probably boring you now. If I go back to my code, here's a piece of code somebody has made. Let's call it the supplier. If you want to use the code, fire away. But the contract is that when you replace a drawable thing by your class, it must have a draw function. So every client, consumer must provide a draw function. That's the contract. Otherwise, you get a compile time error. We'll see in a moment. Okay. Do you want object-oriented programming or generic? It depends what you want. And I can't give you an answer at this moment in time, because you need to practice, you need to have experience before you can give an answer. If I give you the answer, you'll probably say to me, well, I don't believe you, or it's, I don't know, maybe not. So you have to start, you can live without generics, because you can simulate inheritance. You can simulate inheritance with generics, and you can simulate genericity with inheritance, which is what many of the gamma patterns, the gang of 4 patterns do. We can mix the two paradigms using inheritance and aggregation. So you can inherit a template class from a template class. There's no problem. You can aggregate template classes, and the object-oriented is runtime. Is runtime. In other words, it supports subtype polymorphism in the form of these virtual functions I've told you about already, and generic programming in the form of parametric polymorphism. So here's a very simple example, and I will actually run you the code in a moment. But let's say I want a function called max. It's already an STL, but that's not what I'm worried about. I just want to find the max of two numbers, but of anything. So I've got two on the of anything. Anything means n. It's normally a numeric. N is as though like a hint to say it's numeric, but n is not a class. It's just anything. It's just an abstract name. So my function is max, of course. I've got two input parameters, const references. You should know by now what it is. If you don't, you should go back to your slideshow in C++. I've got x and y, which are two n's. And I want to find the max. The return type is either x or y. So the return type is an object of type n. I say if x greater than y, I return x. Otherwise, I return y. So that's fairly easy. So you see here, the contract really here is, you look at the code now, you see the operator, this is a binary operator, x greater than y. He's assuming, he's not assuming, this is the contract, that x and y can be compared. In other words, the type n has an operator defined greater than. If you call this function with your own types which do not have the operator greater than, it will return an error message, compile time error. And I will show you in a moment. I'll work with two strings or something, and just for fun, just a real-time demo, keeps me fit as well. Okay, so it's an implicit assumption here. It's called the contract. Now let's take a very simple example. The code I will run in a moment. So you give two numbers d1 and d2. What would you like, max or min? So if the answer is A, we have a max value of d1 and d2. You see that d1 and d2 are integers. The max function, you see I've got a brackets here, int. What am I saying? Your max function depends on the parameter n. So strictly speaking, let me draw it here. Strictly speaking, let me do it at the bottom, it's okay. So strictly speaking, max is not your function. It's max with its underlying data type. Okay. So in the good old days of C and C++ and MATLAB and Fortran, we only had functions like max, which accepted doubles. But now we've got a max function which depends on a parameter n. And when we run it, you have to tell it what it is. N has been replaced by int. So you're giving the compiler a hint as well. Have I got my pen here? You're giving the compiler a hint to replace the generic type in the declaration of and the definition of the max function by int. Okay, so let me go to the actual code demo. I think it's a good idea. So I've got a project here up and running. So I've got the generic inequality CPP. This is my project file, and I've got a test program. Let me go to the test program. So again, it's the same as before. He's asking you for two numbers. So give the first number, give the second number. Do you want the max or the min? And if you choose for the max, I'm choosing d1, d2. All right. He's actually got a string here. Actually, already, I'm taking the max of a string anyway, which is what I did in another demo. Okay, so just let me change it here. You've got this code as well, so you can run it yourself. Okay, so let me see. Yeah, I've commented out. You see here I got an error here. You see he doesn't know what D1 and D2 are. Yeah, of course not, because it's commented. Okay, so let me just run it to see what happens first of all, and later on I will explain it. Just make sure I can compile it. You don't want to be talking about code which does not compile. Takes some time. It's a bit slow. It's the oh, I got an error. Oh dear. Okay, so let's do some real-time debugging. Yeah. Redefinition. Okay, that's a good. You can see it as an exercise now in learning how to resolve compiler errors. So D1 has been redefined. Oh, see if oh yeah, because it's a string. Silly me. Okay, so let's rerun it again, see if it works. Just a remark, it's good that we're getting some compiler errors, positive thinking, because working with the when you work with template classes and template functions, compiler errors tend to be more difficult to resolve than just good old object-oriented code, and that's because yeah, you got template parameters which are a bit more tricky, of course. But my advice would be to you to build up your classes step by step, template classes, and not write 20 million functions and hope that everything's going to compile properly. Write one function, two functions, and compile. Okay, so here's my function which gives the maximum or the minimum of two numbers, 23 and 42. What would you like, min or max? Maybe max. 42, pretty clever, eh? And I've got a min and of three numbers here. You see, it's just a hard-coded example. We'll show you in a moment how it came about. Now I'm going to do something which is wrong. I just want to generate an error message. I'm going to say okay, I'm going to say D1 and D2 are still integers. I'm going to find the max of two integers, but the function I'm using is going to be a max of a string. So you've got apples and oranges mixed together, so it's not going to work. You see immediately, because D1 and D2 are integers, you have to have a max of an integer. The data type has to be an integer, not a string. But I'm doing it just for fun, because these are the kinds of error message you will get when you start programming in templates, or can get. So where are we? Let's see if we can read it. Cannot convert parameter 1 from int to string, yeah? Which is fair enough. So what do you mean parameter 1? Basically D1 is your parameter 1. He's expecting it is an int, and you're expecting a max of a string. So you're trying to put the integer into a string. It doesn't work, of course not. And that's the nice thing about it. Compilers give template code gives compiler errors, which is good, not runtime errors. Okay, so let's look at my generic inequalities. Again, I've got the my functions here. So I got a function called max. You see, depending on the numeric underlying type. I haven't used end here. I've used numeric. It's a bit more readable. And of course, the min function I've created. I can have the max of three numbers, just for fun. So it's the max of a max, of course, and the min of three numbers is a max of two numbers consecutively, recursively, let's say. So it's all fairly easy. And the example of the last example. So here, for example, max of three numbers here. You got the numbers here long, right? So this was our first example and first meeting, first encounter with the generics. We'll get into real nitty-gritty in a moment. Okay, the summary is C++ supports generic programming model, and in other words, you've seen an example already of a C-style function, just a max function, but the input arguments are not doubles or specific types. These are generic types. Later on, in the next section, you'll see how to create a generic class, which is called template class in C++. It's the mindset is the way you have to start thinking about it. The generic programming is based on abstract data types. So there's a data type and operations, algorithms on the types. I must say the developers are more familiar with object-oriented programming than generic programming. This is a problem, in my opinion, because the future of C++ is going very much in the direction of generic programming, and in particular STL, standard template library, which is it's enormous boost to your productivity, and the boost library itself, libraries which are completely template based. Now, generic programming, does it exist in other languages? The answer is yes. C#, for example, is called generics. If you know C#, it's C# generics is certainly not as advanced as C++ templates. Java has in my opinion, an attempt to support generics. I think it's in version 1.6 of Java. I'm not sure, but as far as I can see, it's just an ordinary wrapper around the Java objects. So, but I don't know. It feels less flexible. I know for a fact, because I work on C# as well, the things you can do with C++ templates are much more extensive than what you can do with C# generics. At a certain stage, when you want to do something fancy, it just breaks down in C#. That's my opinion and experience. Okay, so we've given the summary. The quizzes, some quizzes now, some quick questions. Think about an array class with generic underlying types and matrix classes with any underlying type. So let's say in the good old object-oriented way of programming, I want to have many classes. I want to have a matrix class of doubles, I want to have a matrix class of float, and I want to have a matrix class of integers. So how many classes do I need? How do you do it? And if I'm using generic programming, how many classes do I need? How can you emulate C++ virtual functions in generic programming? The next question is an example. A range is an interval. So for example, you've got a range like when you're modeling stochastic differential equations or a lattice model or a finite difference model, 0 to t. So you've got an interval from, well, in general from A to B, and the range could be time. So from 0 to your expiry time, for example. It could be an interval of your stock price, which has to be discretized and so on. So what would you like to do with ranges? As I've said, in the next section, I will actually go through the source code of range and show you how we've created a class called range. So it's an interval, and it will be used later on for finite difference methods. Describe how generic programming can be used to help us avoid creating class hierarchies. It's sort of related to the first question. Okay, so we'll take a break here and we'll get back now in a moment to some more detailed stuff. It's good that you start thinking about generic programming because it's going to be very important. It is very important. Okay, so we'll see you later. Bye.